Our next module is going to look at how to execute a C program. So when we have, as mentioned, when we have our source code, our C source code in a .c file, this is not executable on its own. So we need some other software, some system software, to process that text file and build us an executable. That process of going through the source code, processing it, parsing it, turning it into an executable program involves 4 essential steps. Those 4 essential steps are pre-processing, compiling, assembling, and linking. Now, these 4 things are 4 distinct processes that happen when we are building our executable. Many people refer to this entire process as compiling the code. As you can see, compiling is only one of the 4 steps of building the executable, but this is often just called compiling because that's, in many cases, the most important step. So let's go through these 4 parts of this process and explain each one in detail. So the first step is pre-processing. And what the preprocessor does is it does essentially 2 things. It handles the directives, these are called preprocessor directives, things like using the #include to include a library. The preprocessor will actually go and fetch the contents of these libraries and embed them into the source code. So our very small number of lines of code in our Hello World program will actually become a much larger program than just those couple of lines of code, because the preprocessor is going to go fetch that library code and put it into our source. It's also going to remove any content that the compiler doesn't care about. So the preprocessor is essentially preparing the source code for the compiler, which is the second tool that's used. So now that we've essentially gotten rid of unnecessary content, namely comments, and we've fetched all of the library code, all of the external code that we need, the compiler will then take that preprocessed source code and it will parse all of the source code, and it will use a particular machine specification to convert the C language source code, which is machine independent, into assembly code, which is machine dependent. Now, there are 2 different ways this can be done. The compiler can actually create assembly code for the machine that it's running on, or if you give it a different machine specification, it can do what's called cross-compiling. A compiler can actually create assembly code for a different platform, for a different machine. So you can compile code on one machine and potentially execute it on a different machine. So again, the job of the compiler is to map things into the platform-specific assembly language, whatever the local machine or the target machine has as its machine instruction language. So the output of the compiler will be assembly language instructions or assembly code. The third part of C program execution is using an assembler. This is performing the assembling step. This essentially parses the assembly instructions that the compiler output and converts them into binary object code or machine code. So the object code or machine code is actual instructions, encoded instructions that can be fed directly into a processor, directly into a CPU. So this is mapping yet another layer of abstraction down from assembly language, which is still somewhat human readable, into object code or binary code, which is only readable by a very small number of humans. It's not intended to be human readable, it's intended to be machine readable. So the output of the assembler is essentially code that could directly be run by the machine. Now the last task is an important one, and this is called linking. The linker, which performs the linking step, makes sure that all of the information needed to execute the program are now combined into a single executable. And a linker, for our purposes, the linker essentially provides two guarantees. The first guarantee is that the executable program has a unique entry point, which means when the system goes to launch this program or to run this executable, it can give control at the exact entry point where we want control to start, which is our main function. So the linker guarantees that each output executable has exactly one unique main function as its entry point. The second guarantee that the linker provides is it guarantees that any name that's used in any part of the program has been defined uniquely somewhere in the program. So we already mentioned there is a unique main function. The second guarantee says any name that we use anywhere in the program is unique and it exists within the program, which means if we want to call a function in a library, the implementation of that library function needs to be part of our executable program. So people often say the library is linked into the executable. This is the job that the linker is providing. This essentially guarantees that when the program is run, everything that's needed to run the program is there as part of the executable program. Ideally, it doesn't have any dependencies elsewhere on other software. It has everything it needs within the single program to do all of the tasks that it needs to do. There are exceptions to this, of course, but from a software standpoint, we just want to make sure that everything is contained within the executable. So now with these 4 steps, you can basically see how we go from source code, from very simple source code, through these 4 steps to an executable program that we can actually run. And of course, we have many different examples of assemblers and compilers and preprocessors and linkers that we can use. In this course, we're going to focus on one of them. We're going to focus on what is called the GNU Compiler Collection. The GNU Compiler Collection, or GCC, was originally designed, it was originally called the GNU C Compiler. That's what GCC used to stand for. GCC is essentially a suite of build tools, execution tools, compiling tools, linking tools for a whole bunch of different programming languages. It's one of the go-to open source tools for doing C programming because that's how it started. There are a lot of other command line build tools that can be used for C programming. Many of them were designed based on shortcomings or issues or difficulties with using GCC. Because GCC is very powerful, very generic, sometimes it's a little bit confusing. There are some compilers that are just much simpler. So by default, if we run the GCC command on a .c source file, it will run all 4 of the required steps, and it will create for us an executable program. So by default, preprocessing, compilation, assembling, and linking are all rolled into one single command. And in many cases, that's what we want. So if we actually open up a terminal and go into the code for this module, 1.2, we can see that I have the source code of our hello.c file here. And I can open this and I can verify that this is exactly the same as what was shown in the previous slide. So I have the hello world program. I have included the standard IO library. Let's run this. So like I said, by default, when we run the GCC command, it will run all of the steps, preprocessing, compiling, assembly, and linking. And if we now look at what's there, we now have a new listing, a new file in our listing, highlighted in green, which by default here that means it's an executable. If I actually look at the more detailed printout, the more detailed listing of my files, I can actually see that my original source code is 89 bytes. My executable is over 15 kilobytes, and it is in fact marked as executable. So we can see that this is our executable program that was the output. And we could actually run this. So if we actually run our executable, we can see that it does exactly what we want it to do. It prints the greeting to the terminal. And then it ends because it reaches the end of the main function. So this is the intended behavior when we want to execute a program. If we just want to build the program from start to finish, the GCC command will do that on its own. We can also tell the GCC command to only do some of those intermediate steps. So let's go back and talk about those in a little bit more detail. So as mentioned, the GCC command will create an executable. By default, it will name that executable a.out for no particular reason or for historic reasons, unless there is an error that prevents it from succeeding. So there are a lot of different ways that we can have errors. Let's actually go and create some and demonstrate what those errors might look like. Let's go in and create an error. The easiest way to create an error in C is to delete the semicolon that's supposed to be at the end of every command. Save that and go back and compile it. And in fact, now it tells us, hey, there's something wrong with your program. I can't create your executable. And it tells us what the error was and where it was encountered. GCC is known for giving somewhat useful error output, but not always the most useful error output. In this case, it tells us exactly what's wrong. There's a semicolon missing on line 5 before line 6. So it tells us where something is missing and where it encountered something that was unexpected. So we can tell that this error is coming from the parsing step of the compiler because it's parsing through the file and looking for what characters are valid. So of course, depending on the nature of the error, we will get different kinds of compiler errors that will prevent us from building our program. Again, we can fix the error, run it again, and see that our compiler is now succeeding and our program would execute. So of course, depending on what the error is, depending on what the compiler is trying to do, it will run different steps. And GCC has tons and tons of options. There are a lot of different flags that you can give it to request different behaviors. Now, if you want to go into the documentation, you can go into the Linux man page for GCC. This is several thousand lines long of documentation. It's essentially, it's a book. GCC is very complex. But one thing that changes is GCC is running the preprocessor, compiler, assembler, and linker steps because we're giving it a .c file. It knows that it's C code because of the file extension, because of the suffix that's there. If we change that suffix to something different, it's going to run different tools. So this suffix is important. We need all of our C code to end with .c. So let's go into a little bit more detail on how the GCC tool actually works. Suppose we just want to run only the preprocessing step. If we just want to preprocess the source code and see what the preprocessor is doing, we can do that. We can actually use the -E flag in GCC, and we can see what is the output modified source code that the GCC preprocessor is giving to the GCC compiler. So if we, instead of running the complete toolchain, the compiling toolchain, if we just run the preprocessor and then we redirect this to a text file or a modified C file, we can see how the preprocessor is affecting the code. So in this case, we can look at this and we can see the preprocessor is actually adding a lot of content. This is now 744 lines of text. So what that's doing is it's saying, this is the file that I found, and here are a lot of notes for how this needs to be processed by the compiler. So the preprocessing is actually adding a lot of metadata for the compiler, and it's telling it things like, here's where the libraries are located. Here are all of the libraries that we're including through that standard IO include. And if you go down through all of these notes, a bunch of definitions that are used in those libraries, you can basically see the entire contents of the standard IO library are basically being incorporated into this file. Now we only need the the put string function, but we're seeing the entire library included, and then we finally find somewhere in here, we find the one function that we need, the put_s function that takes a string and prints it. And after all of this other stuff that's included, we see our original source code with one additional modification. There's no comment there anymore. So this is where the preprocessor did its two jobs. It removed the comments that we put in, and it added the entire contents of the library that we asked it to include before giving this to the compiler. So that's the job of the preprocessor. We can now also look at the job of the compiler. So if we now wanted to preprocess and compile the code, GCC will do that for us by essentially stopping after the compilation process. So this is asking GCC to take the original C source code, run the preprocessing step, which we just demonstrated, and then also run the compilation step to generate assembly code. So we can look at this as well. We can look at what happens if we just tell it to compile but not assemble or link the code. If we do this, this is going to generate assembly code. And now if we look, we'll see we have a new file, hello.s. So we can look at hello.s, and we can see this is actually assembly code. If you've never looked at assembly code before, don't worry about what's actually here, but essentially this is just what assembly language code looks like, instruction and arguments. And there's now not as much of the structure of our code apparent, but we can see it's still doing things like defining our string that we need, and eventually it's calling the puts function that was in our C code. So all of the content is still there. There is a lot more manipulation of the data going on that you don't need to worry about. But this is the assembly code that's being created by the compiler. Now, if we want to go one step farther, we could actually run the first, second, and third steps. We could preprocess, compile, and assemble to generate the machine code. And we can do that essentially in two different ways. We can either give GCC our original C code, or we can give it the assembly code because we've already done the preprocess and compile steps to create hello.s. Either of these two commands will give us essentially the exact same output using the -c flag, which is simply saying create the machine code. So if I give this the original C code, we can look now and we see another new file was created. This is called hello.o. .o stands for object code. And this is actually a binary. So if we, again, look at our extended list, we can now see that we have our original source code, which is 89 bytes in size. We have our assembly code. We have our preprocessed source code, which is 18 kilobytes. It's huge because of all that library. We have our assembly code, which is about 700 bytes. This is a huge reduction in size because we don't build in all of the functions that we don't need. We only build in the ones that we need. You get rid of all of that other, we'll say, garbage that was included by the preprocessor. And then when we actually build the executable, it's a little bit bigger in size because we're encoding all of the text into binary for the CPU. So this is about a 1.5 kilobyte binary file that's being created for the purpose of running on the machine. And again, this is not a human readable. If you really wanted to, you could open this as a text file and you could look at the garbled contents. It would not be human readable. It would contain a lot of non-printable characters. You could open this with a binary editor if you so desire. That's a little bit out of scope for us. All right. So again, we can see all of these actual contents and their respective sizes that are created by the different stages of the compiler. So now if we go back, we can basically see that we can put together those different stages, those different phases of the GCC tool, however we want to. And in most cases, what we're going to want, at least for now, is we're going to want the GCC tool to run all 4 of the steps for us. All of the preprocessing, the compiling, the assembling, and the linking for us to create the actual executable. One thing that we'll often do just as a convenience is we will use the -O flag of GCC. And what the -O flag of GCC does is it simply provides a name for the output. So -O means output file name. And if we run the GCC tool on our source code with the -O flag and another string, it will create our executable now with that name. So for now, this is all we need to know about using the GCC build tool. We'll come back to more advanced use of GCC as we need it. For now, all of our source code will be one program per C file. Each file will have a main function. Eventually, we'll get to the point where multiple files comprise a single program, and then we'll need to change how we build those. But for now, this is all that we need. So essentially by the end of Module 1, you should be able to more or less understand the structure and the organization of a C program. You should be able to use the GCC build tool to build and execute C programs. And you should be able to potentially identify errors based on the output from the GCC tool at the command line. In some cases, you might want to try to create those errors intentionally to see what the output looks like, so you can learn what does it look like if this kind of mistake is made, so that the next time I see that error, I might be able to know what mistake I made. So that is the end of module number 1.